our topic of the project, we've decided to do the damp cityscape exploring the urban heat island effect through humidity. Is by my partner Kennedy and me, myself, Daniel. I'll be going through slides one, two, three, and she'll cover her analysis and I'll cover my analysis. So the first thing is, have you ever noticed how the heat of steam that lingers after a hot shower and keeps the bathroom warm even after the shower's over? It turns out that those little tiny water drops that create humidity can hold on to heat. So as we explore the urban heat island effect, which is the effect of when all the aerosols kind of trap the heat in these urban environments and its effects on temperature, we can't neglect the role it has on the key heat demeanor it has, which is, of course, humidity. And so the location of our project we chose was Central Florida because of its urban environment and high humid environment.
That being said, our study aims at answering the following two questions. How have humidity levels within the urban areas changed over the last decade, and how has it affected the urban heat island effect? The time frame will be between 2012 and 2022, and I will be in charge of answering this question. My partner Daniel will answer how does soil moisture affect humidity levels, and how does this affect the urban heat island effect? His time frame is between 2015 and 2023. In terms of background information, one crucial study we found told us that there's a negative correlation between relative humidity and urban heat island intensity. In other words, as relative humidity increases, the urban heat island intensity weakens. The scatter plot depicted here actually reveals that larger magnitudes of urban heat island intensity occur during conditions of high relative humidity, while the highest urban heat island intensity occurred during hot afternoons when the air was much less humid. A second source we analyzed told us that the urban heat island effect can be explained by changes in the efficiency of convection, which in other words is the transferring of heat between land surface and atmosphere, which, funnily enough, humidity can help conduct through water vapor. And essentially, this implies that humidity can help us suppress the urban heat island effect as it allows for convection to actually occur. Finally, a third source we looked at explained that there's a synergistic relationship between urban heat island and urban moisture island, which, similar to urban heat island, is related to moisture and implies that higher moisture levels are found in areas of higher vegetations or what there usually are more rural areas. And it explains that although plants do help with the urban heat island effect by allowing for convection to happen through water vapor and evapotranspiration and other plant processes, it does increase the urban moisture island as a result. In terms of what we did to conduct this study, I sourced my data from Florida Climate Center's monthly climate reports, specifically for my air temperature data, and sourced my humidity data from Weather Underground's monthly reports. I then took this data and calculated monthly averages in Google Sheets and created an ArcGIS slider map using this data showing the last 10 years. Then I created a time series graph and regression graph for both relative humidity and temperature. And finally, my partner Daniel made use of SMAP data to create regression graphs comparing soil moisture and humidity, soil moisture and land surface temperature, humidity and land surface temperature, and finally, a Google Earth Engine layered map to depict all of these data sets. It's also important to note that he sourced both the land surface temperature data from Landsat satellite data on Google Earth Engine, as well as humidity data from Google Earth Engine. Moving on to my analysis, as you can see on the left, this is the average relative humidity over the last 10 years, and it does seem to be fluctuating a lot, but seems to be on somewhat of a decline since 2017. It oddly peaked at 89% in June of 2017, which could be explained by some sort of climate event that occurred in Orlando, Florida. However, it is important to note that drier air usually means higher temperatures, as we've established. So the expectation is for there to be higher temperatures around this time as well. And that is somewhat what we see. Overall, temperature seems to stay pretty consistent. It stays above 75 degrees Fahrenheit and actually peaked in July 2016, around the same time that relative humidity peaked, which is certainly a good sign. And it has been slowly increasing, very slowly, since June of 2017, which does support the relationship we established earlier. Moving on to my time series graphs and regression graphs, as you can see on the left, here is my regression graph comparing the average temperature and relative humidity. And the trend line seems to be steadily going down, which I did not expect. It basically goes against everything we learned up until this point. And it pretty much shows us that as relative humidity increases, the temperature actually decreases. That being said, we should consider that the R2 value is 0.278. And to clarify, the R2 value tells us the reliability or the strength of the trend line in showing us the relationship between both data sets. And given that it's a scale between 0 and 1, the reliability of this trend line isn't very high. Moving on to my time series graph, as you can see in the box area, we get an exact point that explicitly shows us a point where average temperature was increasing and relative humidity was decreasing, and later on, relative humidity was increasing while average temperature was decreasing, which again supports the relationship we established before. It is important to note that given that temperature has stayed pretty consistent across all 10 years, it kind of seems like it's indifferent to humidity, almost like it doesn't really care about it, doesn't really isn't really affected by it, which does put into question what we know. Finally, here are the scatter map visuals that I created. As you can see on the upper one, overall the humidity levels seem to be decreasing since 2017, as established earlier, while temperature has been gradually increasing. But prior to then, temperature was steadily increasing, but hit a plateau in 2016, and after that there was a large spike, and then decreases to a more reasonable amount. Thank God. And since then, humidity has been mildly random until 2017. And most importantly, if you view both maps in relation to each other, you can see that at the start, humidity always seems to be smaller than temperature, which does help enforce the relationship we have established. And all the other data sets and graphs and observations we made previously.
So continuing on from where Kennedy was, um, so as you can see, this is my question I had to answer, and that was how does soil moisture affect humidity levels, and how does this affect the urban heat island effect? So the urban, as Kennedy explained probably, that the urban heat island effect is not just only about heat. It's also a combination of multitude of things such as humidity, soil moisture, and etc. But my specific question is, how does soil moisture affect humidity levels? Because as explained earlier from Kennedy, the humidity actually plays a big role in the urban heat island effect, and it also raises the humidity. So I used Google Earth Engine, as Kennedy explained as well. So these are some of the visuals just to see how it is. You can see the land surface temperature, the soil moisture, and the humidity as seen. And slide. So we have the linear regression graph. That the linear regression graphs are very, very, very linear, and it was very surprising, extremely, extremely surprising. because it was extremely surprising because you would expect to see a fluctuation from each graph, especially from the soil moisture versus humidity. Now, if you can see that, it's very small. But the soil moisture versus humidity, you can see that as the soil moisture is the same, however, the humidity increases along the way. Yeah, so it shows a direct correlation. That also shows that it's it influences each other through the water cycle, and through that water cycle, it also affects the urban heat island effect. So you could say that due to more moisture, you would expect that the land surface temperature to increase, and that's exactly what happens. You can see in the bottom where it says humidity versus land surface temperature, you can see that the humidity overall is in a stable place, but the land surface temperature keeps increasing due to humidity being at a stable place. And you, but however, it just cancels out with that amount of moisture, with the high amount of heat. It increases at times, and then low decreases um, at times as well. So you could say that's a constant fluctuation. It goes high, really, really high at one point, but then lowers down really low. For example, one day can be super hot, and the humidity is super low. However, in turn, that causes soil moisture to decrease. That causes soil moisture to decrease, allowing for the land surface temperature to increase. However, because of that, it allows the humidity to rise, causing more rain and then lowering land surface temperatures. And on top of that, there's many factors that play a hand. For example, the area that we chose was Central Florida, also known as Orlando, and it has a multitude of things that affect it in place, such as green spaces and giant urban heat islands, just like Orlando and Disney, basically. So uh, those two kind of conflict each other, but at the same time, that's why it's kind of linear. And the next graph will explain it completely. As you can see, the time series chart shows exactly what I was talking about. It goes up, then down, up and then down, up and then down. Because on those days and months, it just goes up, then it goes down, up and then down. Because there are days that just fluctuates, then it goes down, then it fluctuates and then goes down. Because due to the just a multitude of factors. But the main reason is because of the high the high humidity that's there as well, present in Florida, and also the land surface temperature that's there. That's always battling each other and causes this kind of wave on the land surface temperature. So it's always this wave sort of thing. Always this wave. Even during cold months, it's kind of this wave always. So to answer the question, how does soil moisture affect humidity levels? Uh, with higher soil moisture comes higher levels of humidity, and with those higher levels of humidity, it also affects the land surface temperature. But in doing so, they're in, they're inversely proportional, just like a graph in math. If you look it up, it's just like a map. It's inversely proportional. So as the humidity goes up, so the land surface temperature goes down. But in doing so, the sorry, let me take that back. Because the temperature increases, it allows for a decrease in humidity. But when the air becomes drier, the temperature decreases, and then the air will increase in humidity again due to soil moisture. So it's all inversely proportional, and it's all affected together. And it does affect the urban heat island effect. For and it can actually increase sometimes, but decrease. It can also decrease as well. So so it's all generalized.